In the previous class, we learned about the set associated cache. So actually, when we learned about the cache organization, so I said we learned about the direct match cache, which means that we assume that one cache set includes only one cache block. But in the previous class, we learned about the three different kinds of cache organization. The first, the direct map, and then the second is the set associative cache. So we can say that this is the n way. So the n means the number of blocks in a single cell, and then the third is the fully associative cache. So when you learned about this direct mapping cache, the cache has the multiple entries, okay, and then actually these entries are blocks, but we assume that the actually cache one entry of cache can include multiple blocks. So it's actually these entries, so these cache entries, this cache entry is called set, right? Set. And then in order to access the target set of the cache, we can access the target set using the set index. Okay, so address of the load or store instruction, we can use the part of address field as the set index. Okay. So direct mapping cache means a cache has one block per set. Okay. So which means this set can be mapped into the multiple memory blocks, but when these memory blocks are requested by a processor, actually this set can only contain one block. Okay, so which means if this set is already applied by the previous request, then another memory block is requested to occupy this target set, then this previously allocated block need to be evicted. So it's kicked out from the cache. Okay, so evicted from the cache. So this is the direct match cache, because in a direct match cache, the cache can include only one block per set. So actually we discussed about the performance of the direct match cache and the set associated cache and the fully associated cache. So disadvantage of the direct match cache means that if the multiple memory blocks are mapped into the targets of single target set, then this block need to be evicted for the next request. So which means that the cache miss rate can be increased. So in order to increase the performance of cache, then we need to increase the heap rate. Right, because we learned about the performance of the processor considering the cache miss rate. So actually we learned that the base CPI is decided by the ideal case, is the heap cases, and then CPI is increased by miss cases. So in order to increase the performance of our processor, then it means that we need to, when we consider the performance of a memory hierarchy, then it means we need to increase the performance of a cache, and which means we need to increase the hit rates of the cache. Okay. So in the previous class, we learned in the direct match cache, the cache miss rate can be higher than the other set associative caches or fully associative caches, right? So set associative cache means that in a one set, the set is also accessed by set index. So in a one set, the, the one set can include multiple cache blocks. So n of the set associative cache represents the number of blocks that can be included in the single set. Okay, which means if we use the two-way set associative cache, and we can, which means that in the one set, this cache can include the two blocks. Okay, the two-way set associative cache. So if we use the set associative cache, then the number of sets. So if the cache size is the same, okay, the cache size is not determined by number of cache blocks, right? But NA set associated cache, one cache set includes the n block. So which means that if we use the NA set associated cache, the number of sets need to be decreased, right? If the cache size is the same. So this is the example. So this example shows that the cache has the 8 blocks. So if we use the direct map cache, then this direct map cache has the 8 sets because one set includes the one block. So if we use the two-way set associative cache, then one set includes the two cache blocks. So which means that this cache includes 4 sets. Okay. So if we use the NA set associated cache, the number of sets is decreased. But if we, as we discussed about using this example, the cache miss rate can be also decreased. So which means that the performance of cache can be increased using set associative cache. And then fully associative cache means that it's actually the fully associative cache has only one set. Okay, there is no set in the fully associated cache. So which means that actually there is only one set in a fully associative cache. So in a fully associative cache, the number of blocks. So actually, the number of blocks in this one set of the fully associative cache is equivalent to the number of total cache blocks, right? So it's the fully associated cache. So if the cache blocks, the total number of cache blocks cache block is 8, then as you can see, the fully associated cache has the 8 different blocks. Set. Okay, so fully associated cache, actually using the fully associated cache, there is no address field for the set index because only one fully associated cache has only one set. So actually the tag occupies the entire address field except the block offset, right? Because it's a fully associated cache. And then actually, in order to check if the cache block exists in cache, then we need to check every block in the fully associated cache. So which means that the fully associated cache requires the n comparators if our cache has the n blocks. So which means that the fully associated cache needs to check the all tags stored in a cache. So I said that the fully associated cache is the most expensive cache because we need to use more comparators for this fully associated cache.
블락 수가 많아지면 한 번에 있는 데이터가 많아지는 메모리 액세스할 때 클락이 증가하는
블락이 많아진다는 건 블락 넘버가 블락 사이즈가 이게 커지는 게 아니라 블락 개수가 블락 카운트가 많아진다는 거예요.
병렬적으로
병렬적으로 읽지는 않나요? 이때는 그러니까 캐시가 캐시 액세스 cache, the request is given to a cache, and then cache miss happens, then only one block is allocated to the cache. 그러니까 블락 개수가 많아진다는 거지, 블락 사이즈가 많아진다는 게.
그러면 있는 속도는 차이가 없는데.
Okay. So this is so I briefly explain about the hardware organization of the set associated with cache using this example. So this is the example of the four-way set associated with cache. Okay, so which means, so as you can see, this cache has the 256 sets. Okay, so which means that 8 bits are allocated as the set index. Okay, and then as you can see, the last, the LCB2 bits are the block offset. The block offset determines the size of a single block. Okay, so which means because the block offset in this cache, the block offset is 2 bits. So which means the block size is the 4 byte. Okay, so each block size is a 4 byte, and then in a one set, 4 blocks can be stored. Okay, so what is the number of total block? What is the number of total number of block in this cache? The 4, because there are 4 blocks per set, and then there are 256 sets in this cache. So this cache includes the 1024 blocks. Okay, and then the block size is the 4 byte. The cache size is the 4 kilobyte. Okay, so actually this cache size is same to the direct method cache size we learned. So actually, I mean this one. So we can see the difference in this direct method cache and then four-way set associated with cache. So I said the cache size is the same, it's a 4 kilobyte, but because with this direct method cache, the direct method cache has only store 1 block per set. So which means, so this direct method cache includes the 1024 sets. Okay, 1 times 1024 sets, and then each set includes the only 1 data block. Okay, but the four-way set associated cache, one set for different blocks can be stored. So which means we also need to store the tags. And then this is also another different part. Another thing, so when the address is given to this cache, then we can access the target set using the set index, address field. So in this address field, the address bits from 9 to 2 are used as the set index of the cache. Okay, then we can check the 4 different cache blocks. Okay, because one set includes the 4 different blocks. So we need to check the tags of these 4 different blocks with the tag part of the address. Okay, the address of the address of load or store instructions. Okay, then if the tags are one of the tags can be same. So if this is the hit case, And if the block is the valid, then this is hit. Okay, then we need to select from the 4 different blocks to read the target block from the cache. Okay. So this is the organization always set associative cache. Okay. So you can compare the other organization of the direct method cache in the previous slide. And then also the set associative cache of this slide. Okay, then actually when we use the set associative cache or fully associative cache, then we need to consider the replacement policy. So which means, so actually if we use the direct method cache, we do not have any choices for the replacement. It is because in the direct method cache, one set can only store one block. Okay, so and then if this set is occupied, and then if the also the cache miss is encountered, the cache miss happens, then we need the cache need to allocate the new block from memory or low level cache. Then this block need to be allocated to the target set, but this target set has already valid block. So in this case, this block is evicted from the cache, and then new memory block, or the block from the low level cache is allocated to the target set. This is how the direct method cache replace the cache block. But so there is no choice. So the previously allocated block is evicted from the cache, and then the new block is allocated. But if we use the multi-way set associative cache, then a target set can include the multiple blocks. And then if all blocks are valid, okay, then let us assume that cache miss happens, the cache miss. So in this case, the new memory block or a new block from the low level cache need to be allocated to the target set. Okay, target set. Then problem is that we need to select which block is replaced in this case. Well, there are multiple blocks. Multiple blocks are already occupied in the target set, and then if the new block needs to be allocated to the cache. So in this case, we need to evict one of these valid block from the target set, and then we need to allocate this new block. Then which block needs to be evicted from the cache? This is the cache replacement policy besides the which block needs to be replaced in this case. So, and then also I also briefly mentioned in the previous class. So actually most of cache use the LRU replacement policy. So LRU represents the least recently used. So what does that mean? So actually, cache is accessed, then if for the hit case, then this block is used by a processor. And then if the miss case also, the new block is also allocated to the cache, and then this block is used by a processor. So use means then the block in the cache is used by a processor. So recently, if this block is recently used, then we can say that because of the temporal locality. So I said that the locality is very important concept in the memory system. So because of the temporal locality, we can say that if this block is used by a processor, then the same block can be also reused by a processor in the near future. That is the temporal locality. So, which means if this block is recently used, then we can say that, oh, this block will be reused in the near future with a high probability. So, which means LRU replacement fallacy means that least recently. So, if a certain block is not used for a long time, for a long cycles, so it's at least recently used, then this block is evicted from the cache. And then new block is allocated to this evicted place. Okay, this is the LRU. Okay, so which means if we use the set associated with cache, then the cache needs to know the order of accesses. So which means that each block is so each block is recently used or each block is not recently used. So which means that the cache needs to decide the priority of replacement. Okay. So usually the cache use the least recently used LRU replacement policy. But LRU replacement policy is also, it can be also complex for hardware implementation, because it means that we need to also check some access time for this cache, access history for the target cache block for the if we use the LRU replacement policy. So some processors such as ARM use the random replacement policy, which is that among these 4 blocks, the evicted block is selected randomly. Okay, so ARM processor actually employs a random replacement policy for their cache hierarchy. But it is known that if cache employs the random replacement policy, the cache performance is lower than the LRU replacement policy. Okay, so if we use the set associated with cache or fully associated with cache, and we need to consider the replacement policy. Okay, multi-level cache. So when I explain about the memory hierarchy, and memory hierarchy looks like this, and then this the highest place is the register file, and then there is the cache, caches, and then main memory also. So we can find the storage, the control system. This is the memory hierarchy. But when I mentioned about this cache level, the cache has also level on cache, level 2 cache, or level 3 cache. So which means that the caches can be organized with the cache hierarchy. So there is Atom cache. Atom cache is very fast, but the size is small. So, and then after that, there is a low level cache called the L2 cache, the level 2 cache. And the size of the level 2 cache is larger than the size of L1, but L2 cache is slower than the L1 cache. And then also the most modern processors has L3 cache. So L3 cache is it's very large, but it's also slow. So then why do we use the multi-level cache? So I said that L1 cache is very fast, okay, but it's slow. No, it's very fast, but its size is very small. So why do we use cache? So we want to store the frequently used data in the cache. But if this cache size is small, then we cannot store many data. Right? We cannot store a large amount of data in the cache. So even though the error cache is fast, then the size of the error cache is small. So which means if the processor has only error cache, and if data is evicted from the cache error cache, then the data can be found in main memory. So main memory is very slow. So that's why we require the multi-level cache, like the L2 cache. So L2 cache is faster than the main memory, right? Because each cache may be located inside of a CPU chip. Because if the memory is included in the CPU chip, then this memory is very fast. Okay, but we know the main memory is the external memory. So which means the main memory is connected to the CPU chip via PCB line. So it's very slow actually. So we cannot increase the number of this PCB line. It's very expensive. So L2 cache size is larger than the L1 cache, so which means that L2 cache we can store more data. But L2 cache is slower than the L1 cache. So when we learned about the 5-stage pipeline architecture, then we assume that the heat time, the memory access time is only just one cycle. Okay, it's very fast. But enough to support the one cycle of the heat time, then the size of the error cache needs to be very small. Okay, so which means we cannot store many data in the level of cache. So if we can have the level 2 cache, the low level cache. So let's see the impact of multi-level cache. So this is the example. So CPU, the base CPI. So it's the ideal CPI is 1, then clock rate is the 4 gigahertz. So which means that the clock period is the 1.25 nanosecond. Okay. And then let us then miss rate per instruction is the 2%. And then main memory access time is the 100 nanoseconds. So what is the miss penalty in this case? In cycle. What is the miss penalty? The miss penalty, so the main memory access time is the 100 nanoseconds. So in this cache organization, the error cache, and then it's the main memory, it's the processor. So miss penalty means it's the required clock cycles for a missed key, right? So because the main memory access time is the 100 nanosecond in cycles, it is the 400 cycles, right? Because the clock period is 0.25 nanoseconds. So this is the miss penalty, the 400 cycles. And then miss rate per instruction is rate per instruction is the 2%. So for this case, the CPI, this is the ideal CPI, okay? And then we can add this penalty by this miss case. So this is the 0.02 multiplied by 400. So effective CPI is 9. So which means the miss rate is actually very low. So that's 2%. But because the main memory is very slow, and then because of this low main memory, the effective CPI is 9. So which means if we just consider the cache miss case, so it's a non-ideal cases, then the performance the performance of a CPU is slower than 9 times slower than the ideal case, right? 9 times slower. It's just this rate is this rate per instruction is just 2%. It's very low. Then, so let us assume that we add L2 cache, okay, L2 cache. As you can see, the access time of L2 cache is the 5 nanoseconds. So it's slower than the L1. So when we in this example, let us assume that the hit time, the hit latency of the hit time of the L1 cache is the 1 cycle. Okay, but if we see this L2 cache, then the access time is the 5 nanoseconds, it's lower than the L1 because the access cycle for L2 is the 20 cycles. Okay, it's slower than the L1 cache. So the access cycle for L1 cache is the 1 cycle, but access cycle for L2 cache is the 20 cycle. It's 20 times slower than the L1. But as I mentioned, the L2, the size of L2 is larger than the L1. So we can reduce the miss rate. So let us assume that the miss rate in L2 is the 0.5%. Okay. So what is the miss penalty? So which means this cache looks like this. This is the processor. Now this is L1, and then L2, and main memory. Okay. So which means when a processor accesses L1 cache, there are 2 cases: a hit or miss cases, and then for a miss case, then the request is given to L2. Okay. So if also this request can be hit or miss. So for this error miss case, then this data request data is found in L2, then this penalty is the 20 cycles. Okay, this is the miss penalty for L1, but this miss penalty represents this is miss in L1, but this is hit in L2. Okay. So then also for this miss case, the miss penalty from L2 is the 400 cycles because the process this request needs to access main memory. So what does that mean? This is the effective CPI. So it's 1, and this is the miss penalty. So this miss penalty represents there is a miss in L1 and then hit in L2. So this miss penalty is the miss rate per instruction 0.02 multiplied by 20. Okay, and then additional miss penalty from L2. This miss penalty is caused by memory, the main memory. So this is the effective CPI for the multi-level cache. It's 3.4. So if we use the multi-level cache, then the speed up is the 2.6. If we just use the one level of cache, the only level of cache, the effective CPI was 9, but it's reduced to 3.4. So the speed up is the 2.6. Okay, so this is the benefit of the multi-level cache. So what is the benefit? If we use the multi-level cache, then we can store more data, the more data in the low-level cache. So actually, it's obvious that the low-level cache is slower than the add-on cache, but the cache L2 cache or low-level cache is faster, so faster than the main memory. Okay, So this is the benefit of the multi-level cache. Okay. So the primary cost cache is the Aaron cache. So actually, when we design the Aaron cache, we just focus on the hit time, because if the data is hit in the Aaron cache, then this data should be immediately provided to the processor. So which means, we just when we design the primary cache, the Aaron cache, then we just focus on reducing hit time. So we try to reduce the access latency of Aaron cache. But L2 cache, so actually the L2 cache is filtered by Aaron cache. So primarily the request to the memory is firstly filtered by L1. Okay, and then if for the miss cases, then this request is given to L2. So actually when we design the low level cache, then we focus on the miss rate. Okay, try to reduce the miss rate using this low level cache. Okay. So actually, traditionally, we just focus on the hit time of the Aaron cache. So actually, the associativity of L2 cache is higher than usually higher than the associativity of Aaron cache, because if we use the more comparator, then also it increases the latency, access latency. Okay. So that's the impact of the multi-level cache. Okay, so I'll skip here. And then, so actually in the slide, so actually the slide is here. So you can find the summary of a memory height. So you can find the summary of some cache hierarchy and memory height here. And I want to focus on this one, source of misses. Okay. Actually, this summary part includes what we learned in the previous classes. Actually, but I want to discuss about the source of misses. So actually, this is called the tree C of cache. It is because the source of misses starts from C. So the first reason of misses is the cold miss or compulsory miss, as a capacity miss, then conflict miss. So actually this 3C is 3C's of cache explain the reason of cache misses. Okay. So why? So this means that why cache miss occurs in a target cache. Okay, so just figure out the reason of cache misses. The first kind of miss is called the compulsory misses, and then it's called also cold miss. Okay, cold miss. So this kind of miss is actually obvious because initially the cache is empty, right? Cache does not have any data if the data is not requested from the processor. So if the data is firstly requested, then this request is always missed. Why? Because there is no data. So this data is not requested previously, and then it is requested first, then this is always missed. Okay, this kind of miss is called cold misses or compulsory misses. So actually, so So actually the data, the cache block is perfectly requested, and you cannot find this data in the cache. So this is the cold message. So also this is also included in the cache message. And then capacity message. So it's obvious that the page size is smaller than the main memory, which means because of this limited capacity of cache, then we cannot store every request data in cache. So because of this limited capacity of cache, then some this data is evicted from the cache, and then when this data is re-referenced, then this data cannot be found in the cache. Okay, so which means, if the cache size is infinity, then this data can be re-referenced and then can be found in the cache. But because of limited size of cache, this data can be evicted before re-reference. Okay, this kind of miss is called the capacity misses. And then conflict miss. The conflict miss means that if we use the fully associative cache, okay, then we can. So actually, the newly requested cache blocks can be allocated in any blocks of the cache. But if we use the set associative cache or direct map cache, then this allocation is limited by this set associative cache or direct map cache. So which means that the cache miss rate can be increased if we use the set associative cache or direct map cache. So this kind of miss is called conflict misses. The conflict misses are caused by lack of associativity, which means lower associativity of the cache. So I said the fully associative cache is very expensive, so which means the most processor do not use fully associative cache. But because of this limited associativity, the cache miss rate can be increased. This kind of misses are called conflict misses. Okay, so there are three different kinds of misses based on the source reason of misses. Then so when we organize the cache, then we can change the cache configuration. So which means that we can configure the cache size. We can change the cache associativity. So we can change the block size. Then what is the effect of this changing? So if we increase the cache size, then we can decrease the capacity misses. Why? Because the cache can store more data. But what is the negative performance impact? So disadvantage is that may increase access time. So if we increase the cache size, then the access latency can be also increased. So which means that the performance cache becomes lower, okay, because the size is increased. But in order to decrease this capacity misses, then we need to increase the cache size. So this is the negative impact. Then if we increase the cache associativity, then we can decrease the conflict misses. Right. So if we use the full if we increase the set associative from 4-way to 8-way, then we can decrease the conflict miss. We can decrease the conflict misses. But if we increase the set associativity, then the cache hardware become more complex, and also it may increase at the time. Okay, and then if we increase the block size, then we can decrease the cold misses. So actually, if we see the actually also, you know, I posted the last homework assignment in the Blackboard. So actually, the first homework question handles this cold misses actually. So in order to decrease the cold misses, we need to increase the block size. Why? 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 So I said the cold miss means that the data is firstly requested by the processor, and then this data is not found in the cache. Okay, so this is the cold misses. But if we increase the block size, then we can decrease the cold misses. How? Why? Okay, go ahead. So if we let us this like this. So if we repeatedly if we access the the array data, so and then we change the index of this array A from 0 to 199. Okay, so if we and then let us assume that the size of this single element of this array A is the 4 byte. And then if we set the block size as the 16 byte, then when the A0 is firstly requested, and this is the cache miss, right? The firstly requested. Then when cache miss occurs in a cache, then cache allocate the 16 byte of data, no cache block, because the cache block size is the 16 byte. So which means 16 byte, the element of the size of the single element of this array is the 4 byte. So which means in a single cache block, this block can include the 4 different elements: A1, A0, A1, A2, and A3. So which means firstly A0 is requested, then 4 elements, because the cache block size is the 16 byte, 4 elements are allocated to the cache. And then in the next iteration, we can access, the process can request the A1, then this A1 is found in the cache. So which means, and the cache miss rate, so even though the A1 is firstly requested by a processor, this A1 is found in the cache. So actually this cold miss rate is the 20. So which means the miss rate for this case is the 25%. Right. Even though the A1 is firstly requested, and so it's because of the large cache block, and A1 is found in the next iteration. So if we increase the block size, then we can decrease the cold misses. So which means if we use the 60 byte of block, then this 60 byte of block includes the 16 elements, right? So which means we can reduce the cold misses, right? But if we increase the block size, then also miss penalty can be increased because more data should be provided from the low level cache or main memory. Also, the cache can be polluted. Okay? So which means if we increase the block size, then this cache will have lower the smaller number of sets. Okay. So this is the performance impact by the cache size and the cache associativity and then cache block. Okay, so this is the end of the cache. Okay. Now we will learn about the virtual memory. So as I mentioned, the cache hierarchy is the part of the memory hierarchy. So we learned that the cache is very critical for the performance of the CPU, right? So and then also there are different kinds of cache configuration. Okay, so that's what we learned in the cache, and then now so we will learn about the virtual memory. So this is actually until the cache. So actually until the cache, so this is the hardware part, but the virtual memory is also managed by hardware, and then also the virtual memory is managed by operating system with the software part, the part of hardware and part of software. Then so actually in the memory hierarchy, so we learned that this is the cache and this is the main memory. And then so this is cache and then this is the main memory. And then load instruction is executed. Okay, the load instruction requires the data using this address. Okay, then firstly we access the cache, and then for the miss cases, then we can access main memory using this address. That's what we learned in chapter 2 and then chapter 4, chapter 5. Okay, the memory hierarchy. Then what is virtual memory? Why is it virtual? So in a computer system, there are two different terminology, like the virtual and the opposite meaning of the virtual is the physical. So physical means that it's real. So which means the virtual means that it's not real. Okay, what does that mean? Virtual memory actually is the not real memory. So what does that mean? So actually this concept may be a little bit tricky because until now, so we handled for some physical world, so it means the real world. So we discussed about the hardware architecture of the processor. So we discussed about the hardware architecture of memory hierarchy, cache. But what is virtual memory? So at the cache, you may think that at the cache, then we can learn about the main memory, right? Because it's the lower part of the memory hierarchy. But now we are learning about the virtual memory. So actually, I will explain about the concept of the virtual memory. So when the computer system is originally designed, this memory, the main memory, DRAM was very expensive. Right. The DRAM was very expensive, but the DRAM size is also very small. So actually, I remember when I first lived the old computer system, like the 88 computer system has around the 640 kilobyte of main memory. It's less than 1 megabyte. Okay, it's very small. So what's the problem? Actually, in a computer system, the DRAM is very small. The size, so the cache size also small, but the DRAM size also very small. But we want to use large DRAM. That is the dream of software engineering, right? We can use which software engineers want to access a large amount of data. But actually, in a physical computer system, the DRAM size is very, very small. And then so which means that the hardware resource of this DRAM is very precious. It's also very expensive. So if you want to increase the size of the DRAM, then you need to pay more than $1,000, so something like $1,000. So it's very expensive, and then the size is very small. So, but when we design a software, then we want access large amount of data. This size of data can be larger than the DRAM size. So how can you solve this problem? When you design a software, design an application, and we want to handle the large data. But this large data cannot be stored in the RAM. How can you solve this problem? So data is large. And then we want to use fast memory. It's similar to cache. Data is large, so we want to handle the large amount of data, but we want to use fast memory. So fast memory is DRAM in a computer system. So how can we solve this issue? So data is large, and then we want to use fast memory. This concept is similar to cache. Why? Why do you use cache? We want to use fast memory in a computer, in the CPU, but in order to use the fast memory, the size is small. Okay? So even though the software using the load instruction, this load instruction access the data in the main memory, so which means that the data size is very large, but we want to use the fast memory. So we use cache. It's the same to the software application. So software want to use large amount of data, but DRAM size is small. How? We can use DRAM like a cache. Then this large amount of data can be stored in the storage. Right. The storage is very, very slow and hard to describe, but the cost is also very low. Also, the storage size is much larger than the DRAM size in the computer system. So actually, the virtual memory is developed for using DRAM like a cache. Either because DRAM size is small, and for software engineer wants to use large memory space. But our physical memory space is like this, is very, very small. So idea is that so the software we just provide the virtual memory space. So it's actually virtual means that it's not real. It's like a fantasy memory. So to the software engineer, so we just provide the large virtual memory. So for example, 4 gigabytes of the virtual memory space. Okay, it's a very large virtual memory space. Then software can write the code, assuming, oh, we can access this very large virtual memory. But actually, the physical memory size is very, very small, like the values of 1 gigabyte. Then this 1 gigabyte of data, so this space, even the physical memory space can be used as like a cache. So which means that this physical memory, the frequently accessed data is stored in this physical memory. Then and other data is stored in the storage. Okay. So this is the concept of the virtual memory. Okay. So even though the computer system has the 1 gigabyte of physical memory, it's a real memory, but to the software, the software think that, oh, we have larger memory, 4 gigabytes of memory. Then software can write the code with the limit of this memory size. But in reality, the frequently accessed data is only stored in this smaller physical memory space. And then other data is stored in the storage. Okay. This is the concept of the virtual memory. So actually, this the concept of the virtual memory is a little bit tricky because it's not a real space; it's a fantasy world. So, but just try to understand why virtual memory is used in our real computer system. So, I mean, the main purpose of the virtual memory is that we want to use the small and fast DRAM space like a cache. Then to the software, then we provide the large virtual memory space. So software engineers can write the code without considering the limited size of main memory. Okay, that is the virtual memory concept. But you can say that, oh, in the old computer system, the DRAM size is very small. But recently, the DRAM is very large, right? But the DRAM is cheaper than the DRAM is still expensive, but it's cheap, right? But we are still using virtual memory concept. Why? Yeah? The price is big, okay. So another reason is that if we use the virtual memory, then the software engineers do not need to consider memory management. So what does that mean? Actually, if you check the running processes on Unix, Linux, or Windows operating system, then we can find that many applications, there are many processes are running on our computer system. But we know that our computer system has 4 cores or 8 cores. But on the operating system, many processes are running. So for example, we are running the internet browser, Chrome. Okay, so we can run Chrome multiple times, like Chrome A and Chrome B, from Chrome C. So it's the same program, same application, but so we can launch from multiple times. So which means process A, process B, and process B, C's are running for the this same Chrome application. Particularly is actually this is the binary code. So which means that when we write a code, then this code is compiled and then compiled to the binary file, and then binary file includes the machine code actually, right? So which means the load instruction, load A. Let us assume that this binary includes the load instruction. So what will happen? So this is the same binary file, which means that we are running the same load instruction, load A, and load A. What's the problem? Oh, the same load instruction is trying to access the same address of data. But if we launch the application, if we launch the different application, or if we launch the same application multiple times, so actually these applications are accessing different data. So how can we manage this case? So for example, Chrome A, B, C execute the same load instruction, but these Chrome A, Chrome B, Chrome C are using different data. How can we manage this case? So if software needs to manage this case, it will be very complex. Okay? So actually, the software the software so it's a Chrome A. The software, the operating system provides the unique virtual memory space. So which means that the Chrome A, the operating system provides the 0 to 4 gigabyte of memory space. Then, so this Chrome A can access some data with the address A. And then the Chrome B is a different process. The operating system also provides the virtual memory space, like 4 gigabyte. And then this Chrome B also accesses this data using the address A. But I said, this data is the different. So even though to the software operating system provides this virtual memory space, and then using the same address A, in reality, but because this data should be found in the real physical DRAM. In reality, this address is translated into the different physical address. So which means even though this address is the same by Chrome A and Chrome B, the data is different. So which means that in a real physical DRAM, this different data is stored in the accessed by different addresses like B and C. So the virtual operating system changed this address A into the real physical address B for this Chrome A, and then access this data. And then it's also saying, even though this address is the same, operating system changed this address into the real physical address C, and then access the real data. So this is also the virtual memory concept. So actually, recently, this is actually the virtual memory is designed for using the smaller DRAM space, but recently the DRAM size is very large, but still we are using the virtual memory concept. It is because the software does not need to consider real memory management. Actually, the software accesses the virtual memory space using the address A, but this address is the virtual address. And then in a reality, the operating system and then computer hardware change this virtual address into the real address, the physical address to this DRAM, the physical memory. So actually, the data in the physical memory is accessed by this physical address. So which means even though the same binaries are used, but data can be different. So we can access the different data in the real memory. So it may be a little bit tricky because until now, so we assume that when the load instruction is accessed like A, then we assume that using this address A, load instruction access the main memory DRAM. So I also explained like this. But in reality, this address is translated into the real address, like a physical address, like a B. And then using this B, the physical memory is accessed.
원래 뒤에 있던 데이터는 기억이 납니다.
어떤 B? 아니, 원래 B는 리얼 데이터입니다. 리얼 데이터를 액세스하는데 실제로는 소프트웨어는 software access using the virtual address. So software does not consider about this case. So like same address, so different data is accessed by same address. Why? Because it's the same binary file. But in reality, these data are stored in the different space of DRAM. Because it's different data.
because 데이터가 4개씩
아니 그렇죠. 그렇지 않습니다. 오케이. 끝나고 말씀해. Okay. So it may be I understand this can be a little bit tricky, but it's in a real computer system. Actually, the software works like this. So which means so until now we are in chapter 2. Okay, so this one. So this is the memory layout we learned in chapter 2. And then in this layout, we learned that the memory space starts from memory address 0, and then a stack. Stack is starts from the last memory space of using the stack pointer. Right. But I said this is also virtual memory in chapter 2. So think like this. So there are many processes like Chrome A and Chrome B, and Chrome C. So these different processes also has the stack pointer. So access the stack address. The address is the same, but it access different data. So actually, this memory space is the virtual memory space. Okay. And then by operating system and then CPU, then this virtual address is translated to the real address, it's called the physical address. So using this physical address, and data is accessible. Okay, this is the virtual memory concept. So I briefly explain about the virtual memory. So I know this is a little bit tricky because until now, I assume that the memory is accessed directly by address of the load or store instructions. But in reality, this address needs to be translated into the real address, physical address. Okay, so please remember this concept of the computer system. Okay, so I will stop here. Then, so as I will record the video, and then I will post the original video on the YouTube. Okay. Okay. Any question? Okay. Thank you for your attention, and see you in the next class. Yeah.